So hello everyone. My name is Pablo Martinez. I'm a senior software engineer in Huawei, and today I will be talking about how we can parallelize indirect memory writes applications in MLIR automatically. So let's start with the question: what is an indirect memory write? Basically, an indirect memory write involves writing to an array where the access is based on indices stored in another array. So on the left here we have the example of a histogram computation where we basically load the index in IDX from an array. And then we use that index to access the second array, which actually stores the data, which is histo. In this case, we are basically accumulating over the histo array. So the problem with this kind of computation is that it cannot be parallelized normally with a normal Pragma OpenMP parallel because of the indirect memory writes, you don't know beforehand the location that you are going to store. So it could happen that many threads are accessing the same memory address at the same time. So we need like more specialized techniques to parallelize this automatically. So why are indirect memory writes important? So we can see this kind of patterns in many applications, many AI and HPC applications like between centrality, triangle counting, and unsorted segment sum. And the thing is that when we want to run these applications in MLIR, we normally would be writing this in a linear generic and then lower that into lower dialects. And the problem here is that you cannot actually represent these kind of applications with only a linear generic. So here we have a linear generic representing a matrix multiplication or just a random kernel. But the thing is, we cannot actually make this for an indirect memory write because you need to load the index that you are going to use, and then you need to use that index to actually access the data. So how can we parallelize these kind of applications in MLIR automatically? Our approach is basically because we need to express this with SCF for loops. So our approach is basically, so here we have an example about how can we express this with loops. So this is an indirect memory write application. Basically, we have the arg0 in the index that we are going to loop over with the loop. So in extracted, we basically extract the index from the indices. Then in line 3, we use that index to cast into the index data type. And then we finally access the buffer, which is buff in line 4. And in this example, we're basically adding 1 to each of the elements inside the buffer. And then finally, in line 6, we are inserting this element that we just added into the buffer again in the same index. So here we can see that we have an indirect read in line 4 because we are using IDX, which comes from the another array. And we have also an indirect write in line 6 because we are also using this index to access the buffer. So our proposal to parallelize this application automatically is to first add a tiling operation at the loop level, because currently we can tile at the linear generic level, but not at the loop level. So we introduce loop tile using for all. And then we use another option, a new option, which is called privatized buffers, which is able to translate this into MLIR so that many threads can access the computation and make it work properly. So here we are going to see an example of basically the code that I showed you before and how this would work with only one thread. So here we have the first array, which stores the indexes, and the second array A, which basically stores the data that we want to compute. And in this example, we are going to iterate over the data, and we are going to add 1 to each of the elements. So for the first case, we need to go to index 2. We load the previous value, which was 0. And then we load the element in A, which was the 2. So we add 2 plus 1, and we store the 3 inside the array C. The same for the rest of the elements in the array. So here, for example, we can see that in this case, we need to go to the index 7, where we had 0. So we load the A, which is 1. So 1 plus 1, 2. And Here we need to access, in the next iteration, we need to access again the same position. So that will be reading the previous value and then adding 2 plus 1. So here we can see that we have an example of we are accessing the same memory location so that many threads could be, this cannot be parallelized like normally. So how can we make this in MLIR? The high-level idea is basically that we are going to create private buffers. So in this example, we have 3 threads, and we have C1, C2, and C3. And then we divide the iteration space of the loop between these threads. So for example, thread 2 would be only accessing indexes 2, 10, 0, and 7, and would be computing this program and storing the values in C1. Then thread 1 would be storing the values in C2, and thread 2 would be storing the values in C3. And then once we have these partial results in C1, C2, and C3, then we can reduce the partial results and generate the final destination, which is in C. As you can see, the results are the same as we would be running this application in sequential. So how does it work in MLIR? First of all, we need to create an empty tensor where we are going to store the private buffers data. In this example, we have 8 threads, so we create a tensor of 8 multiplied by the original value of the original size of the array. Second of all, we are generating a SCF for all, which is going to iterate over the 8 threads that we are generating. And we also need to generate the SCF for all in parallel at the end. So inside the SCF for all, we need to access the index of each private buffer, like the private data of each buffer, with the index using the SCF for all. And then once we have the position where each thread is going to be writing, then we need to fill that buffer with the neutral element, which is usually a 0. And then next one, we need to insert the SCF4 inside. And basically here we will be using the private buffers that we just created. And then at the end, we need to reduce all the partial results into one single result. So for the evaluation, we have evaluated 3 different applications: triangle counting, between centrality, and unsorted segment sum. So the approach is to have the C++ code, convert this into MLIR using polygeist. Then we apply our loop tiling and privatized buffer approach, and we run the program. And we have used the Kunpeng 920 with 32 cores. So for the triangle counting, we can see that we have a decent speedup. And we can see here one of the problems with this approach is that for the big input, we actually ran out of memory because the original buffer was so big that when we need to replicate this for the 32 threads, we run out of memory. For the between centrality, we have almost perfect speedup, near optimal scalability. And for the unsorted segment sum, we have a good speedup, but limited compared to the other 2 applications due to the duration, like the execution time of the reduction at the end. So the limitations of this approach, first of all, is that it does not support conditional writes. So in the case of the histogram computing, as you can see here, we need to check if the current value of the histogram is less than the maximum value of an int 8. So with the approach that I showed today, basically we would be generating a linear reduce, which does not take into account this condition. So this is something that we are currently working on and will be supported in the future. Second of all, the memory usage is increased, as I showed you in the example in the evaluation. So, for example, with 32 threads, we would need 32 more time the memory of the original buffer to compute the same application. And lastly, the reduction has a big impact of the execution time because it's not parallelized. It's a sequential part of the application. So that's something that we are also working on because we will be in future where we are going to be working on the parallelizing the reduction, which can be done in MLIR automatically. And we will also support the conditional writes. And more importantly, we would like to upstream this contribution so that all the community can benefit from the automatic parallelization of this kind of applications. So that was everything from my part. Thank you very much. Any questions?